In this lecture, we are going to begin discussing recurrent neural networks. Let's first think about why an RNN would be useful. First, as usual, we are going to start with our dumb as possible approach. What is the simplest thing we could do? Let's think back to how we approached image classification. Before we learned about CNNs, which are specialized for looking at images, we used ANNs. We were able to do this because we took an image and we just flattened it into a feature vector, which is the only type of data you can pass into an ANN. Recall that this goes along with our motto, all data is the same. It doesn't matter if your feature vector is a flattened image or some data you collected in a survey. The ANN doesn't care. So let's consider whether we can take the same approach now. In fact, we already did when we looked at our time series forecasting model. We just said pretend t is d and pass that n by t matrix into a linear regression model. The model has no idea what you're passing in as a time series. It's just doing the same algorithm it's always done. But here's the question. What if your d is not 1? In other words, you have a multi-dimensional time series. Recall that one example of this is if you work at Neuralink and you've implanted multiple electrodes into your brain. Now you have multiple recordings at every time step, making it a multi-dimensional time series. Well, here's an idea that requires pretty much no imagination at all. Why not flatten this data too? Let's take a t by d matrix and turn it into a t times d sized vector. Let's say you have 5 electrodes in your head, and you make a recording with sequence length 100, so 100 time steps. Then, if you flatten this, you would just get a vector of size 500. In fact, this is even easier to visualize than a flattened image. Here we just have 5 different time series signals. Now all we're going to do is concatenate them together and say it's one big vector. Easy peasy. Alright, but we already know that this approach is possible, and we've pretty much done it in code already. If you're confused what I mean by that, it would be pretty much the same as our MNIST script, which at this point is pretty simple compared to what we've done so far. So let's go to the next step and think about why that might not be a good idea. The first problem is the same as with CNNs. If you were to do a full matrix multiplication, it would just take up way too much space. If d equals 100 and t equals 10,000, which by the way is not unrealistic, then all of a sudden your flattened feature vector is of size 1 million. You probably don't want a 1 million size feature vector going into your ANN. As with CNNs, RNNs take advantage of the special structure of the data. An ANN is the most general. It just connects every input to every feature. Every feature, in other words, is directly composed of every single input. We know that for images, this is not really a great idea because we're actually looking for very tiny patterns relative to the full image. The question is, in what way can we exploit the structure of a sequence? Here's the idea. We can take inspiration from forecasting. We know that to predict the next value, past values are useful. But what if we apply this to the hidden feature vectors? So let's take an ANN, where the hidden feature vector is calculated from the input vector. The output is then calculated from the hidden vector. Now, to make an RNN, all we need to do is make the hidden vector loop back to itself. In other words, the hidden vector depends not only on the input, but also on its own previous value. This is just like our very basic linear regression forecasting model, where the prediction was just a linear function of past values. Now, we are saying the hidden state is a nonlinear function of past values, specifically that the nonlinear function is a neuron. As a side note, the loop back implicitly assumes that there's a time delay of 1 step. Alright, so how do we calculate the output of an RNN? Well, we use the calculation you see here. As you can see, there's only one new thing. The hidden state h of t now depends on the hidden state at the previous time step as well. Also, x, y, and h are indexed by time, but that should be a given. Some other assumptions we've made here are that we're using the sigmoid activation for both the hidden and output layers. This is of course not necessary, but we need to write something down, so that's what I decided to write down. As usual, the output activation is dependent on the task being done. So a sigmoid for binary classification, nothing for regression, and a softmax for multi-class classification. Another assumption is that this neural network only has one hidden layer. In fact, with RNNs, this is pretty often the case. You could stack up more hidden layers, but I don't see that too often. As usual, you'll want to test that out on your particular dataset if you think it might be a good idea. It's helpful to name these weight matrices so we don't get them confused later on. Luckily, it's pretty intuitive. The reason we call WXH WXH is because the input is X and the output is H. So we call this the input to hidden weight. The reason we call WHH WHH is because the input is the previous H and the output is the next H. So we call this the hidden to hidden weight. B of H we call the hidden bias. And finally, WO and BO are the output weight and the output bias. The important thing there was to differentiate between WXH and WHH, since they are both weights belonging to the recurrent layer. As a side note, this layer itself has several names. The most common name is just the simple recurrent unit. But since this has been studied in the past, it's also associated with a person, and so it is also known as the Elman unit. Alright, so for most people, these equations are pretty intuitive, but for some it's not. So let's just be super clear about how we're going to calculate the output prediction given a sequence of inputs. Actually, this will help us uncover some hidden details that we need to consider that are not obvious at first. First, we assume that we are given a sequence of input vectors, x1 all the way up to x big T. Each individual x is of course a vector of size d. So this entire sequence would be stored in code as a matrix of size big T by d. In math, however, we assume that we are working with individual vectors. So let's start with x1. From x1, we can calculate h1. But wait, now you see one of these hidden details that you probably didn't think about. h1 depends on h0, but what is h0? In fact, we refer to this as the initial hidden state. Typically, we just set this to an array of zeros, but it can also be a learned parameter. In other words, you can learn this vector using gradient descent. In PyTorch, it's possible to make the initial state a learnable parameter, but it's simpler not to, and in fact quite conventional. So in this course, that's the approach we're going to take. Alright, so now we have h1. From this, we can calculate y hat 1 using the usual neuron formula. Next, we consider the input vector x2. From this, we can calculate h2. h2 depends on x2 and h1. We just calculated h1, so that's not a problem. From this, we can calculate y hat 2. Now, we can repeat this process to calculate h3 and y hat 3, h4 and y hat 4, and so on, all the way up to h big T and y hat big T. Okay, great. That all makes sense. By the way, if you found that a little confusing, don't worry because we are also going to do this calculation in code as well, just as a little extra practice to make sure you understand how it works. But here's something you probably noticed which is strange. Why do we have a y hat for every time step? If we are doing something like forecasting, we only want to predict the very next value. If we are predicting something like the sentiment of a tweet, we only have one answer, positive sentiment or negative sentiment. So what is the purpose of having a y hat for each time step? Each of the y hats depends only on the x's up to that point. The answer is that for these types of problems which I just described, all the y hats, except for the final y hat, are ignored. So y hat of big T gives us the final prediction, and all the previous y hats are discarded. You can think of them as like temporary variables. At the same time, there are cases where we would want to keep all the y hats at each time. One such example is neural machine translation. In neural machine translation, both your input and your output are sentences. They are just sentences in different languages. In this case, both the input and the target are sequences, and therefore, you need to capture the predictions at each time point. Considering neural machine translation, let's think about how we can reason about what an RNN is predicting in probabilistic terms. If you recall, when we look at ANNs, and hence this also applies to CNNs, that the output prediction after applying the softmax function is a probability distribution. For a regular ANN or a CNN, it's the probability that y equals k given x. X is the input vector, or in the case of CNNs, an image, and y is the label. For neural machine translation, this is also classification. We are trying to predict a category, which is a word, in the target language. So the question for RNNs is, if we are doing classification, we will have the probability of y of t equals k given something. But what is this something? One picture that helps us to understand this is the unrolled RNN. This is like a block diagram of all of our calculations and their dependencies. First, we can see that h1 depends on h0 and x1. Y hat 1 depends on h1, and therefore it indirectly depends on x1. h2 depends on h1 and x2. Y hat 2 depends on h2. Thus, y hat 2 indirectly depends on x1 and x2. Similarly, y hat 3 depends on x1, x2, and x3. Y hat 4 depends on x1, x2, x3, and x4. Finally, y hat 5 depends on all the x's, x1, x2, x3, x4, and x5. In general, we can say that y hat of big T depends on every x in the input sequence. It should be clear from this picture that each y of t overall depends only on the current and past values of x. So what does this mean in terms of the probability distribution that the RNN is modeling? The probability of y of 1 equals k given x1 is the first distribution. But now, notice that y of 2 depends on both x2 and h1, which in turn depends on x1. So we write the probability of y of 2 equals k given x1 and x2. Next, we have that the probability y3 equals k given x1, x2, and x3. And this pattern continues all the way up to the probability of y of big T equals k given x1, x2, x3, all the way up to x big T. Now, this is not that important in and of itself. You're not really going to be manipulating these probabilities or doing anything mathematically. But it's interesting if you've ever studied Markov models. The idea with the Markov model is that they make the Markov assumption. What is the Markov assumption? It's easiest to understand with words. The Markov assumption says that the probability of the next word depends only on the current word in the sentence, but not on any previous words. You might think, that sounds very unrealistic. For example, if the current word in a sentence is the, how can you possibly predict the next word in a sentence? The next word could be any number of words. So Markov models are pretty weak if you use them that way. Now consider an RNN for predicting the next word in a sentence. So we're modeling the probability of x of t plus 1, the word at time t plus 1. Then our output distribution is the probability of x at t plus 1 given x of 1, x of 2, all the way up to x of t. As you can see, the RNN accounts for all the previous words in a sentence, rather than just the most recent word. This is one reason why RNNs are so powerful for modeling sequences. As a final thought exercise for helping you understand RNNs, let's write some pseudocode that would give us the y-hats at each time. First, we have to consider what we're given. We're given the initial state, h0, and the weights of the RNN. So we have wxh, which maps from x to h. We have whh, which maps from the previous h to the current h. We have b of h, the bias term for the recurrent hidden layer. We have wo, the output weight, and bo, the output bias. And of course, we're also given a single input sequence x, which has the shape t by d. It represents t sequential vectors of size d. Let's assume a tanh activation and a softmax at the output. Okay, so to calculate the output predictions, we're going to start by initializing y hat, the output, as an empty list. Then we're going to set h last, the previous value of h, to h0. Then we're going to loop through each time step from 1 up to big T. Inside the loop, we're going to calculate h of t using the recurrent neuron equation we saw earlier. Then we can use h of t to calculate y hat at time t as usual. By the way, this is just the dense layer. Next, we append y hat to the list of predictions y. Finally, and this step is important not to forget, we assign h of t to h last so that h last always represents the last value of h of t when we do our calculation for the next h of t. At this point, we are going to briefly go back to the biological inspiration for neural networks. Recall earlier when we talked about how neurons are organized in the brain. We can imagine that there's no reason for the neurons in your brain to all go in one direction. In fact, recurrent circuits in the brain have been well studied in biology. The idea that neurons can connect in a loop goes back decades, and personally, I find this topic very interesting. One such example is the Hopfield network. One of the methods used to train Hopfield networks is called Hebbian learning, invented by Donald Hebb. He inspired the famous rule, neurons that fire together wire together, and neurons that fire out of sync fail to link. It's actually quite unfortunate that most people have a very narrowly focused view on deep learning. It would be very interesting to see, if we applied modern technology to these old ideas, what we could discover. The last thing we are going to do in this lecture, now that you understand RNNs, is to ask the question, what are our savings? If you recall, we did this example with CNNs also. The idea was, because CNNs take advantage of the structure of images, we can use shared weights. The same idea applies to RNNs. With RNNs, we apply the same weight matrix to each input vector x of t, and we apply the same hidden to hidden weight for each calculation of h of t. Thus, it's useful to compare how much we would save if we used an RNN instead of an ANN with a flattened time series. So let's do a simple calculation for the ANN. For simplicity's sake, we won't consider bias terms. So let's say that t, the sequence length, is 100, and d, the feature vector size, is 10. Let's say that the hidden vector size, m, is 15. Then if we flatten this, we would have a 1000 length input vector. Correspondingly, we would also have t hidden states. So the hidden size in the ANN would be t times m, which is 1500. Finally, let's suppose we are just doing binary classification, so the number of output nodes is just 1. In this scenario, our input to hidden weight would be of size 1000 times 1500, which is 1.5 million. Our hidden to output weight would be of size 1500 by 1, which is just 1500. Therefore, in total, we have approximately 1.5 million weights. Now compare this to the simple RNN. Remember, we are calculating the size of WXH, WHH, and WO. WXH, since it goes from input to hidden, must be of size D by M, which is 10 times 15, which is 150. WHH, since it goes from hidden to hidden, must be of size M by M, which is 15 times 15, which is 225. Finally, we have WO, which goes from hidden to output, which must be of size M by 1, which is just 15. So in total, we have 150 plus 225 plus 15, which is 390. So if we take an ANN, which has 1.5 million, 1,500 weights, and divide that by 390, we find that an ANN has 3,850 times more parameters, which is a huge amount of savings. Thus, we learned again that by taking advantage of the structure of specialized data, we can create much simpler and more compact models compared to full ANNs.